All right, so we had a long discussion about processes. I want to wrap it up today. Still want to give you some ideas about what's going on with these processes. What I'm staying away, at least until next week, next lecture, is any idea of communication between these processes, right? Whether that communication is through the network or direct communication. I'm still staying away from it because I need to talk in a structured way about all that stuff. So let's see, we talked about difference between extensive discussion about threads, lightweight threads, processes, all of that discussion. All kinds of tricks that can be done with multi-threaded servers. You can pass things around, hijack connections, do all of those things. Virtualization was a really cool thing that we've seen last time, right? The fact that you can simulate a full-fledged operating system inside another one. And that gives you the luxury of, in fact, starting to move things around and logically partition hardware. Right? Logically partitioned hardware was the realm of mainframes for many, many years, and people had to pay enormous amounts of money to get this logically partitioned hardware. You can have it now through VMware-like solution. I mean, there are many other, right, including Linux, low-level Linux virtualization solutions, right? So that's a big, big luxury because now you have this double insulated situation in which the actual operating system that runs user's program is virtualized, so it sits as a process on top of the real operating system. So if the whole operating system does something nasty, it's easy to remove it, throw it away, and start another one, right? You're not going to disrupt the base operating system. And then you have processes within the virtualized operating system. So, right, it's like tools, doubly insulated tools. You don't need a ground for them, right? Stuff like that, right? And this is why they're everywhere in industry. Virtually everybody runs on virtualized machines right now. I mean, one of the main reasons is why not? Because you're really not paying right now with the support for virtualization in the processor. You're not paying any significant price for it, right? The performance degradation is measured in small percentage points, 1 or 2 percentage points at most for most programs. If you are CPU intensive, it's virtually going to be 0, right? Remember, you're not emulating, right? What's an emulator? So let's think about the difference between simulator, emulator, and virtualization now, virtualized hardware. So what's a simulator? It's a program that is going to go and pretend it's doing anything that the hardware does, right? Simulators are usually used by the hardware designers before they build the hardware, right? Then what's an emulator? Well, the emulator is going to try to do a little bit better mapping, to go and map reasonably one-to-one, and just so it has some support for what's already there, but it has to fix little problems. Right? So you don't have some of the, for example, running Windows programs inside Linux with Wine, right? So whatever the application is, that's some sort of an emulator. As long as you're not doing Windows-specific things, you run natively, but when you do Windows-specific things, you have to hijack them and emulate their behavior, right? But virtualization to a large extent, I mean, it has elements of emulation, but virtualization to a large extent is mostly about this low-level hardware support to most of the time allow access to the hardware, but only when crossing some sort of boundaries at the lowest level you want to have some protection, right? And virtualization is by far the best solutions of them all. Right? You can run very close to the performance you would get on the native operating system. Now, of course, if you run Linux inside a particularly bad version of Windows, you're only going to be as good as the bottom operating system, right? Actually, you get the bad properties of both, right? So if you have inefficiencies of a different kind in both, you pick them up, pick both of them up. But I mean, that's not the case with any of the modern Linuxes or Windows operating systems. The kernel is really tight and high performance. Okay. Right. So we talked about these things, how it goes with virtual machines. Now you have pure virtual machines like what Java has, and just so virtualization is a little bit stretched there. I mean, arguably, a virtual machine. Java-like virtual machine gets a little bit too close to a simulator, possibly. If you have a just-in-time compiler, you start doing things closer to emulation and maybe to what the hardware virtualization would be. But I mean, they got much, much better in the last few years. Okay. So you don't really have a big performance hit because of the just-in-time compiler. Now, even ask yourself the following question. What does it take to properly compile something, even in terms of a virtual machine? So what's really the difference between interpretation and compilation?
Compilation outputs native machine code with architecture.
Well, yeah. So at least in the good old days, compilation generated the lowest level code that could run at the lowest level on the machine. and interpretation, right, or right, that you had very high-level constructs, for example, syntax, abstract syntax trees and whatnot, and you walked over them in order to figure out what the code is supposed to do, right? So a for loop really was a walk through a data structure with a condition, and, right? So what's so bad about interpretation? Well, those branch mispredictions, they're horrible, okay? But what do just-in-time compilers do, for example? This is a very relevant issue for what you're doing. So a just-in-time compiler, essentially, instead of doing interpretation on the code, it says, hey, this code is used often enough, so let's take the trouble to generate native code out of this and to do the one-to-one mapping instead of doing interpretation. Because compilation has a big problem. Namely, it takes time to compile. Right? It really takes a lot of time by modern standards to compile. Right? So then you have to strike a trade-off. If you have to run a very short program, you're better off with interpretation, really. And probably you can see this in Scala, right? So in Scala, you fire up the interpreter, it interprets stuff at the speed you're typing it and gets stuff done there. It's going to run slower than compiled, right? Of course, if you compile it and you have a lot of work to do, it's worth it. But I think Scala is notorious for how slowly it compiles things by now, right? But think about all the good stuff it does. That's how I comfort myself, not with Scala, but to me, C++ is too slow. Because in my database engine is part of the execution time, right? You translate high level into low level, and then you compile. And those 7 seconds in which the compiler does something, those get added up to the query execution time, so that's bad, right? I know Scala can do 30 seconds like nothing, right, to compile some of that stuff. Okay? So that's one advantage of Scala, the fact that you can have both an interpreted and a compiled version of it. And Scala is very amendable to compilation, right? Why? Because of the strong typing. So how many of you heard about compiled PHP code? So who does compilation of PHP?
Sorry?
Who does compilation of PHP?
Facebook.
Yeah, so they invented their own little gadget, right? To basically what they do is translate PHP into C++ and then compile the C++. Because PHP was too slow for them because they had, remember those front-end servers? It's all the discussion about how do you, I mean, it's some sort of virtualization if you want. A logical partitioning of your server farm. Request comes in, and then somebody decides which of the many servers you have to get it. But if you have close to 1 billion users, even that starts to be problematic, even if you have very large data centers. So then you're very concerned that you're not producing that HTML code fast enough if you're Facebook. And they invested a significant amount of effort into speeding up PHP. Why not write in C++?
They already had a large PHP code base.
Yeah, you read that article. So they had a large PHP code base, and it's so much better to write in PHP. You don't have all of that super-duper problems that you have in C++, right? By the way, Scala can now generate code, and when compiled, can actually run very fast. So possibly a better solution would be this play framework that works in Scala. Right? It's way faster than PHP at doing things. It doesn't have as big of a following, but right. All right, good. Somebody is reading things about things. All right. So rough architecture of the virtualization. It essentially looks the same way we got used to, except that the, right, I'm sorry. This is the general architecture of a machine: application, library, operating system, and hardware. There are some sort of connections here with the real hardware through the general purpose instructions. Anything that's privileged, remember, it has to go through the operating system. And virtualization adds another layer here. The hardware becomes virtualized hardware, and the real operating system and hardware sit beneath. Let me see if there is a picture here. Yes, right? So application, operating system, then virtual machine monitor, that's that operating system-like behavior at the bottom, and then the hardware. And that is really simulated hardware to fool the operating system in here, right? In fact, mainframes had 2 separate operating systems, one to manage this logical partitioning of the hardware, and one to run the native operating system within each of those logical partitions, right? So if you were reading the news about maybe 10 years ago, maybe a little bit closer to us, IBM managed to run 50,000 Linux instances on top of one of their mainframes, just to show how cool their logical hardware partitioning is. So the virtualization in that circumstance was done by, so this was one of the large mainframes, the Z370, or whatever they are selling now. And on top of it, they had their own toy to do the hardware, logical hardware partitioning, which is basically that virtualization, right? And on top of it, they started to run full-fledged Linux instances. Of course, when the Linux instance runs, it sees only the virtualized hardware. It's constrained by the lower level, the virtualization layer, not to go outside that boundary. And it was running as if it would be alone on the entire system, right? This way, for example, you can actually have extremely fast access to data because those mainframes have fast interconnects. They don't really use better processors. I mean, they use maybe this 5 gigahertz, whatever, the Power 6 or whatever IBM is doing nowadays, right? That's a little bit better, let's say, than the top-of-the-line Xeons maybe. But what you have, it's fast interconnects. We're going to come back to this later, right? So when it comes to applications that are limited by the communication, a mainframe could be the right choice, right? And plus, you had the stunt in which they said, hey, you can run 50,000 instances, which means you can host 50,000 different, let's say, websites that have their own little full-fledged operating system stack, right? A particular danger when you're hosting services is if whoever is designing the software that's actually hosted tries to go outside the boundaries of just the normal languages you provide, like PHP or whatever it is, and start corrupting the operating system. This is why, essentially, any source of hosting now involves virtualization. You run in a virtual machine. Right? So you use virtual machines all the time, just you don't know it. It's happening in the backend servers. That's the way, that's a sane way to keep things apart. Right? And also to cut bigger pies into smaller pies. You're an organization. We are probably going to start doing this, in fact, when we purchase the large cluster. Right? So the department is in the process of buying a large cluster that will have probably, I don't know, in the order of something like 500 CPU cores or something like that. Now, of course, the way to keep sane on that cluster is to use virtualization to give little things everywhere to many, many people. Because then you can just go and kill the entire hosted operating system in the virtual machine if something goes bad, or forget about going bad. This is how you can actually make sure people use the machine only for the amount of time they are supposed to. Right? So instead of going there and trying to kill processes and things, and maybe they corrupted this or they did this, all you have to do is shut down the virtual machine. Or that's how you can charge people. This is what Amazon does with the EC2. You literally provide an image for the entire operating system that's going to run in the virtual machine. Then they say, we don't care. Then they start the clock, and they start charging you, depending on which specific instance you ran. Right? But notice something interesting. So how many people have looked at the spec for how much Amazon EC2 charges, but more importantly, what hardware they have, what virtual hardware they have. So they have a very, very funny thing, right? They are talking about cores. So they say you can get a virtual machine that has 8 cores, 4 cores, or 8 cores, or 16 cores now, with amounts of memory up to whatever, 76 gigs or whatnot. But they have a very funny definition for what a core is. So their core is some sort of an equivalent with, I think, a 1 gigahertz processor from whatever time back. So they're not promising you any real hardware. They say, each of these guys is equivalent to some sort of a standardized processor. Now, which specific processor you run and how, it's our business, and we're never going to tell you. By the way, you see this operating system here that sits on the virtual machine? How does the operating system know on what processor it runs? Right. So there are special instructions to ask the processor, hey, who are you? What are you? But in fact, those instructions can be intercepted, so you can actually fool the operating system, even with respect to what the actual CPU is running on. So when you run in one of those virtual machines, you only see the 8 cores of this strange processor when you're in fact running on a completely different hardware. Right? They are all kind of compatible with respect to what instructions they run, because they cater to the lowest common denominators. You have a little bit of SSE instructions and whatnot, but not some of the newer gizmos. They are now selling better nodes, right? So they say, hey, you can get nodes that can do AVX, or you can get nodes that have graphic processors in them and whatnot. But of course, they are pricing them differently. Right? So virtual machines make it all manageable and all better. And you can fool completely everything. Okay. Now, I do want to spend a little bit of time, because this turns out to be important, because it's happening all the time, in a slightly longer discussion about client-server architectures and how the processes work. Okay. All right. So let's say on Linux, what's the graphic interface based on? X Windows. Okay. So an interesting question is, okay, so what does this X Windows do? So what's going on in there? By the way, Windows has a stranger kind of thing in there, and because they have a stranger kind of thing, they paid a big price at some point, especially when you started to use machines in a distributed way. Okay? So let me tell you, give you a little bit of history, what happened with X, and why is it important? Why am I talking about it right here? So X Windows, basically, I think started to be developed in 1985 at MIT, and it was arguably 10 years ahead of time, but unfortunately 10 years ahead of the hardware as well. So it was very sluggish initially. Some of the decisions they took were extremely forward-looking. Right? So in retrospect, the decisions they took in 85 were in fact extremely good by the 2000, but not necessarily good in 85. So this is one of the decisions they actually took, is with respect to how does a program get something displayed on the screen, right? In general, how do you draw things on the screen? How do you get a user interface? How many of you build user interfaces? Let's get some idea. Any sort of user interfaces, okay. So what are we talking about here? Windows interface. If it's web interfaces, the web browser does all the dirty work for you, so that doesn't count. Windows interfaces, Windows programs. Okay, so you write your program and you have some sort of an API that says start a window, do a window. What does that software do, for example, in Windows? Remember what I told you last lecture? Always ask deep questions, what's going on and what's not going on, right? A lot of these questions are very relevant. Yes? Right, so yeah, but this is why that's potentially problematic, okay? So what you could do is to give access to the specific application to the whole screen, but that's full screen mode, for example, or regions of the screen. So you might decide to do, so in the end, you could say, you write in whatever area you want, and I'll make sure that shows up in the screen. If you write in memory, well, I mean, first of all, that's how graphic cards work nowadays. They use something called frame buffers, and you can write directly in frame buffers and then display the frame buffer, right? So you could play that game. But the X Windows designers decided not to do that. Decided, in fact, to have a full-fledged client-server architecture and to, in fact, make even a local system a distributed system, because that had a tremendous benefit. In particular, what they did is the following. So you had the application. And the application, it's supposed to convince somebody to draw on the screen. But instead of changing colors of pixels and saying change this and that in order to put something in the pixel, which works great if you have an extremely fast communication with whoever displays the pixels, right? What they decided to do is, in fact, come up with a full-fledged protocol that specifies what needs to be done in terms of transformations to the screen. So you could access pixels, independent pixels, but then you had to send instructions to say, change the color of pixel blah into color blah. And it was all relative to something called a window that can be displayed by the server. So application itself talked to some sort of a server. That's usually called the X server. And actually give it instructions that are almost human readable. They are actually quite text instructions. How many of you programmed in something like SVGs, the scalable vector graphics? So scalable vector graphics is essentially a graphic format that specifies how to draw things. But in fact, those are reasonably humanly readable instructions. I mean, it's heavily based on HTML, for example. But you literally have instructions that say, move to this point and draw a line to this point, draw a line to this point, draw a line, and then fill the curve and fill it with whatever pattern. And those look humanly readable in SVG, right? Because so you can have special elements in SVG that are called paths. Sorry. So a path element can have as a value a string, and if in the string you put an M, that means move. If you put an L, that means line. If you put an A, that means arc, right? And you can also say go only vertically or go only horizontally, and then corresponding numbers. And literally, an SVG drawing engine is going to interpret all of these things. They're just shortcuts. You could literally say move to 0, 0, then line to 10, 15, or whatever. Now, X Windows, I'm not going to go into the protocol and so on. I don't remember details anyway. It's similar. You can actually draw things on the screen by giving these instructions that are, in fact, some sort of text instructions. Now, there is a tremendous benefit for X Windows applications if the protocol simply goes in a uniform way on a communication channel between the application and the server. Namely, you can easily put it on a socket, which means some sort of internet connection, TCP/IP. So you can easily have the application on one machine and the server running on a completely different machine. So applications that display things remotely were supported from the beginning in X Windows because they couldn't care less if you talk direct. Actually, you cannot even, there is even no notion of talking directly. There is only local socket versus one of the network-supported socket. Right? All the operating systems, when the network stack was designed, they supported something called local sockets, which means you don't go on any network card to transfer information. The information just goes through the kernel. It's like a pipe. It's a glorified pipe, essentially, right? So let's draw a little bit of the OS stack, right? So this is where the kernel is, and this is where the application is. This is application 1. This is application 2. Now, if you have multiple machines, application 1 could open a normal internet socket. Then the kernel communicates by taking the bits and putting them eventually on the wire, and then it takes them from the wire and makes it all the way to the application. And they resurface here, and this is application 1 prime running on another machine. This is your remote actors, essentially. So remote actor is some abstraction here that gets down to some sort of connection, internet connection, TCP/IP, resurfaces here, reinterpreted here, OK? But you can actually have a high-performance local socket in which you go in the kernel, and this guy knows that you're on the local machine and just gives it immediately to this guy. No network card involved, and it's just moving information from one buffer to another, or not even. Put in a buffer, read from the same buffer, which is equivalent to a buffered access to a file, for example, or a pipe. A pipe is exactly just this. You copy information into a kernel buffer, and from the kernel buffer to the other application. Okay? So local sockets are pipes. Remote sockets are these more complicated internet connections. And the X server couldn't care which one is using. They use exactly the same protocol, okay? Because it's just a stream of bits. You put a stream of bits, and you receive a stream of bits on the other end. Now, of course, the server has to talk to the application as well. Why? If it's running a graphic interface, you better intercept things like keyboards and mouse and whatnot, right? So then potentially you have a stream going back with event stream. So there's an event stream going back, and there is drove this for me stream going this way. Okay? It's a lot more complicated than this because they wanted to save bandwidth and whatnot, and they supported a lot of high-level operations, not only low-level operations. Things like take the whole window and move it a little bit left. Arguably, those kind of operations are supported on Windows as well. But in Windows, it's just a library that manipulates directly the frame buffer, maybe with a little bit of clipping and protection so that Windows don't draw anywhere, and they only draw in their respective window unless they are in full screen mode. Right? But on the X server, it's completely remote. OK, good. So for example, do you know how to run with remotely with a graphic interface? So you have your own Linux installation. You have to, can you log in into a server and run there an X Windows application and have it displayed on your screen? So what do you need to do? Just make sure that the channel of communication is created, right? And that can be done by essentially telling the so by the way, so I have my own Linux machine. I log in into a remote server. Somehow I set things up right. So I run on that server an application that displays graphic-y things. And then they show up on my screen. Where is the server and where is the application? Who runs the X server? Your machine. So it's exactly the opposite of what you expect. The X server is the program that controls the screen. You have the screen. Your Windows installation has the screen, right? And now the application is that program that runs on the remote machine that's actually on the server. So you run the application on the server, and you run the server on the client. But hey, that's X Windows terminology for you, right? OK, web browsers. From the point of view of displaying, who's the client, who's the server? Well, the browser is essentially the kind of server, and the client is probably the JavaScript code or whoever interprets the HTML code that gets to display things. OK, good. So this is just a little hint for you. SSH, you can tell SSH to forward X Windows traffic by doing an SSH minus capital X. SSH can do so much more, port forwarding and whatnot. OK, so SSH minus X and then the rest of the things, credentials and whatnot, will forward and set up a full-fledged X Windows connection. So if you run a program that needs interface on the other end, is going to get displayed on your screen. Okay. All right. Now, if you want, go into details. But the important thing is, and this is why I'm even talking about these things in the context of the classes, because the X Windows designers decided to have this communication through sockets, remote access to machines was extremely straightforward. It took forever to Windows systems to get remote access. And they do it actually in very ugly ways. Right? Anybody has any idea how the remote access works on Windows? No Windows program can survive without an interface. I'm sorry? Yeah, well, Telnet, what was Telnet? What's Telnet? Anybody knows? Telnet was a very low-level program that allowed you to basically log in, is what SSH does now. It's just a terminal emulation, so it's really not Telnet. What is it? Some companies made a lot of money out of a product that could access remotely a Windows machine. The PuTTY, it doesn't allow you. So what you really need is somehow run something on the server, on the Windows server, capture what it would display on the screen, but display it on your screen. Well, VNC is the open source version of that, yes. But the commercial version, right, so is this some sort of terminal server. They were sold on the... Right, so Citrix made a lot of money out of a product that was doing what X Windows was doing for free. Okay? It was doing it in not so good way. And VNC, it's essentially emulating what Citrix is doing with their terminal server, right? So the terminal server essentially captures the frame buffer locally on the server and just transports the frame buffer. X Windows is so much better because it has extremely high-level instructions about what needs to be done, right? So the traffic on the internet that X server produces, it's much smaller compared to the traffic, for example, that a VNC-like tool would produce, even when you use clever compression and differences and whatnot, okay? Because one is low level and it just talks about bits, is the terminal emulators, terminal servers, and the other one is high-level instructions to paint on the screen with a very, very powerful, in this case, server, okay? But essentially, every time you use any graphic interface in Linux, you have client-server stuff going all the time through the local sockets, right? So, and most importantly for us, they live in different processes. They're completely isolated from each other. And not only that, but you can have multiple applications connecting to the same server, right? And the server polices everything and makes sure that everybody plays by the rules. And if they don't, what can the server do if an application doesn't play by the rule? Cut down the connection, wipe out any things that were related to that connection that affected the screen. In particular, eliminate the window, because all of them are window-based systems. So as an application, in principle, what you do is you get a window in which you run. But it's the server that controls the window. So if you're not nice, it knocks you out, removes resources with respect to your window, and then as an application, you can send anything you want on the wire because the X server is going to ignore you. That's great. It makes for a much more stable system. So then you produced a nice form of isolation between the application and the X server, so one can die without the other. Now, if the X server dies, you're in trouble, right? Because all those applications are going to be confused. It's very hard to design non-confused applications. In principle, you could do this. And we know that that's working on the web. The application could detect the connection with the X server. If the X server died, it's to say, oh, not again. OK, let's start from the beginning. And it starts repainting everything as opposed to giving only deltas. Right? That does happen all the time when you're talking about web clients. You have to assume that somebody closed the window by mistake or did something, right? So always have the ability to rebootstrap the entire display. X servers tend to be very stable, so nobody I know of bothers to write applications that can repaint themselves on the screen. Usually you kill it and you start it again. But in principle, you could, okay? Because it's just a connection. You could watch for that connection going down and open it again. Right. So a lot of these principles of distributed systems were there in a lot of these programs that got used over and over again from early times. And this is why the performance hit. By the way, this is a story about why sometimes distributed system techniques are not the right techniques, right? So in X Windows, why was it slow in 85? Well, because it is inefficient. You're talking instructions through some sort of a socket as opposed to putting bits in a frame buffer. So this is why Windows got snappy very early on. And by the way, this is how it got a tremendous market share. All the Unix vendors, right, had extremely lousy extremely lousy graphic interfaces. So the reality in about 1990s was this. You paid $5,000 to $10,000 for the privilege to run one of the Unix systems, and it was sluggish. Or you paid $100 and you got a Windows system that looked pretty and you could run it. Right? All that because of the X server. But the reality by the 2000 was you couldn't really do serious remote access based on Windows servers, but you had it for free and in a very elegant way on anything that was based on Unix, in particular Linux, which by then killed all the other Unixes, more or less. Right? OK. So this is, to some extent, what is happening in there. Right? Application middleware, local OS, communication, and go back with the application-specific protocol. In this circumstance, X server is here, and the client machine is here. Of course, the X server is itself some sort of an application. It uses libraries, so it has middleware, and it runs on top of the OS. It's just that usually it runs in a privileged way to get access to that low-level frame buffer that Windows gets access to in the first place. And that essentially means low-level control of the video card. Right? That is, in fact, a privileged access to the video card. Well, why does it have to be privileged? So the frame buffer is basically a memory region, so that if you put something in the memory region and then you tell the card, hey, this is the active frame buffer, it gets displayed on the screen. Why would that be privileged? Because otherwise, applications will trample over each other, right? If you don't go through the OS or you don't police it through the OS, applications trample over each other. So what you have then is a nice operating system in which, in the back, they don't destroy each other. They just mess up what shows up on the screen. To the user, that's as good as being bad, right? So you have to police everything, including what gets displayed on the screen, ability to kill things, get rid of them, whether they want them or not, and so on. So it has to be, displaying on the screen has to be a privileged instruction as well, and has to be policed through some sort of mechanisms. And none of the video cards I know of can play the role of the server, in which you could, in fact, in hardware, provide an isolation. And then the operating system would just program that. That's essentially what's happening with the more mainstream kind of computation. It's not that OS, it's all the time on to police it. It programmed the hardware to police it. And when something happens, special code gets run to see how to deal with it. Right? But video cards don't have that. So then you have to go through a single application that controls the frame buffer, which usually has some sort of root privileges on that. Okay. Yeah, this is the typical scenario with the X Windows system. Okay. Now, one thing we are going to do in this class is talk about distributed systems, protocols, techniques, so on and so forth. And one neat idea, for example, would be to try, so we talked about all those kinds of transparency, things like, the most important one was failure transparency. So if the operating system, if whoever implements the server can watch for any defects and then fix them by maybe restarting another one in place, right? Then you could potentially mask those failures. Let's take, for example, your project. So in your project, you had basically on every machine, you had the boss and workers, and they were doing job. And then maybe a super boss if you did the bonus part. And the super boss is going to give instructions. But suppose I go and I kill one of your machines, or the machine simply becomes unavailable. Then what? Oops. That portion of the space never gets explored. Well, it could get explored in the following way. You could basically start to get a little bit smarter. And maybe this is a cute project in which the big boss knows that the sub-boss is not doing necessarily any work, but is the only way to communicate with the workers, and is the only way to make sure that he's still alive. So what they could do is exchange messages, let's say once a second, right, in order to ensure that they are alive. If the big boss sees the local boss not being alive, it could assume that the whole machine is down, right? And then simply try to find somebody else who can do the work that this entire set of workers should have done, right? And you can even mask any kind of it wasn't really dead by putting some data structure, doing some bookkeeping. And even if later this guy comes alive and says, oh, I was actually doing work, you can say, you know what, I already gave it to somebody else. I'm going to ignore what you're producing, and somebody else is doing this work for me. So in that way, you could completely mask failure in one of the worker nodes, and the high-level user that just said, hey, start this range and give me the numbers with a certain property in the range never knows where things run, how they run, and if any of the subparts died and got resurrected. So in fact, what you have done is some form of hijacking, some form of monitoring, if you would do that. You monitor, and if things don't go right, you delegate to somebody else. Maybe one boss that already reported that, oh, I've done all the work you asked me, so you just bundle it up with extra work for those guys, right? So you have many choices, especially if you implement things with actors, that wouldn't even be that hard to code, right? So maybe I should do a bonus on top of the bonus to say, hey, if you do this super cool thing, right, and then we kill some of the workers, see what happens, that would be even a super bonus. Or, right? Hey, you can do it for kicks, if nothing else. That's my suggestion. But you see, you're already getting, when you're talking about this client-server environments, and when you're playing with the actor model, you're already getting to situations in which you could do a very sturdy kind of computational network. How many people know about SETI at home? So what's SETI at home? Right. So on a high-level, high-profile description is looking for signals in the noise of the space to see if there are intelligent signals. But at the lower level, it's basically run this computation for us, right? Here is a problem, run the computation for us, and return the results of the computation. So suppose you have to design the software for SETI at home. Well, it's essentially very close to what you're doing for your project, okay? Except that you could design it better, because SETI at home was done 10 years ago. It's not particularly nice, right? But you would definitely be interested in, did you do the work I asked you to do? Because if you didn't, I'm going to give it to somebody else, right? So some sort of failure masking there would be very nice, because you can't expect hundreds of thousands of people, millions of people, not to ever have failures. Okay? Most of them don't even know what they are doing. They're just excited, and then they say, oh, I started the program, they close the laptop goes to sleep, and everybody is happy that it's in. While sleeping, the laptop is doing the work, which is, of course, not happening, right? Right. Now, in general, getting, especially this handover, right? So we talked about these handovers when it comes to basic things you can do with processes. You really need low-level support for this kind of things, right? So you can do handovers. So somebody is watching only for connections, and then when a connection is established, you hand it over to one of the possible workers. This is a very basic functionality if you want to, in fact, scale at least reasonably even on one machine. You have multiple cores. You better be running multiple things in parallel, right? What I want you to understand is you don't necessarily need to design a single process, a single application that does everything. Using inter-process communication or inter-process protocols, you could get all of them to work together. It's as if, well, you already did that if you did the bonus part of the project. You got essentially separate processes to collaborate with each other through this external messages that could look like internal messages, but nevertheless are external messages to actually get the job done, right? So in particular, what you could do to test, for example, your ability to run with multiple separate computational engines is to start 10 processes on the same machine. And remote actors work through these local sockets anyway, like they are remote sockets. And you could fully emulate those 10 machines on your single machine. Of course, you're not going to get the performance, but you're going to get the debugging, right? If you want to debug your ability to resist failures, you can go and kill the process by hand and see what happens. If the big boss figures out in the right amount of time, if it detects the failure, max the failure, does whatever it needs to. I mean, somebody has to deal with the failure. You cannot mask the failure by ignoring it, right? Because the work doesn't get done in that space, right? And we talked about this. This is a typical architecture for a really large installation, right, in which you have the client request. There is always some dispatching, but nowadays it's essentially happening in the router, in the front-end router. The request is dispatched to multiple servers that pick up the request and do things, and they might access one or more databases to actually get persistency and whatnot, right? Of course, if you're Amazon, what's happening here is completely crazy. I mean, you're talking about millions, tens of millions of simultaneous connections that you have to take care of and hand them over to somebody else. Now, you see, from the point of view of a really powerful router, it's not a problem to deal with that many connections, right? Routers nowadays, especially the expensive ones, right, the really, really powerful routers that Cisco is building, can easily deal with 100 million packets per second and with millions of connections open per second, right? So it's not so much even a bandwidth problem, because they have enormous bandwidth in those routers. It's a matter of, if you don't do the correct distribution here, if you don't have the right architecture in the back, you have no chance to keep up with the speed of the front router, right? The front router is going to be thousands of times faster than satisfying the request for any of the machines. And if you don't do it in hardware, for example, what you could say is, I got a stream, I send it to a server, and the server dispatches it. It turns out that that server is going to be overwhelmed at such a scale. And then the solution, I mean, let's talk about the general approach, but maybe that's a better idea, right? So when you have, you start with a little system, you get the basic functionality going. Maybe not even so much a client server, you do it in a single application. Then you say, hey, I want to go a couple of steps higher, so you got maybe, you spread the functionality between multiple servers, and you get maybe a little bit of load balancing, but one of the servers is going to be designated as the head, the boss, and do the load balancing. If you grow much higher, you have to move then these decisions with the load balancing into closer to the hardware, right? So you move to solutions that get you closer to the hardware, like routers, right? But knowing that it's possible to do this kind of dispatching at the level of internet connections, right? Then you could design even your intermediate solution to do dispatching on internet connections. This is basically what Apache does all the time. You get a connection, and it can fire up another instance that runs and picks up that specific connection, right? And in fact, a lot of the solutions in the routers were designed to pick up the work that normally a front-end server will do. The front-end server gets now overwhelmed. It has too much. You design hardware like the router. Now, why would you do that? Why would Cisco care about taking the load and solving problems that the front-end server has? Oh, it's always about money, right? It's a business opportunity. You design the toy, you can sell it to Amazon for a lot of money because now they are desperate. They cannot grow beyond a certain point, right? If you don't do this low-level hijacking, it's exactly similar to hardware mechanisms. There is only so much you can do at the higher level, so much you can do in pure software. If you don't get close to the bare metal, you will not be able to solve the problem beyond a certain point, right? So it doesn't matter how well you write that front-end server, how much you strip it off, whatever you do to it. You, in fact, have to get close to a hardware solution to be able to really do what Amazon needs to do. In particular, hijack millions of connections that could pop up in every second. Oh, by the way, there is an internet connection for every picture on your screen. When you load an HTML page, right, every resource has a separate internet connection. Now, servers are trying to bundle up multiple resources on a single internet connection, right? But you're still doing a lot of separate internet connections, even to display what you would perceive as a... So you're not connecting when you go the first time on a website, really. You're connecting every time when you send some information, most of the time. They are moving now toward... So distributed system question. This has to do with communication. You already have seen some of these things, right? In order to communicate, you have to do what? Open some channel of communication and communicate on the channel and then take it down. Okay. All of this have to be done properly for the system not to go haywire, right? Good old days, every single resource opens up a separate TCP IP connection. You want to now design applications that are better. Better can mean two things. Better can mean a better experience for the user, but that always boils down to not having too sluggish a thing. But also, that's also tied with not too much pressure on the back end. So how could you relieve the pressure on the back end and provide a better user experience at the same time? Well, sorry. Right, so if you could play your cards right and set things up so you have a single connection, you can put everything on that connection, you might be in a much better situation, right? Okay, good, but how do you do that? Because the trouble is, it's also a server issue. For example, Apache really likes a new connection. Every time you go to another URL, so maybe you grab all the images because they are subsequent calls to that URL and try to piggyback things on the same connection, but at some point you have to give up. Well, you could at least, I'm sorry?
Saving it in browser caching.
Well, you can do caching and so on. That's the classic technique that you deploy for distributed systems. But when it comes to purely communication, and I'll tell you in a second why that's important. what you could do is essentially design applications with JavaScript and whatnot in the front end that simply open a communication channel. These are called WebSockets. How many people know about WebSockets? Okay, so we have a bunch of people here. Good. So WebSocket is basically a permanent connection you can open, and then you have permanent communication between the client and the server. I put something on a connection, comes up, but we don't really open it. We actually have to watch it because it stays up so long that you might even forget that occasionally it can go down to remember to open it up and watch it when it goes down, right? That's what I have to do in mine now because every now and then somebody decides to take it down, right? But it stays up for hours, for days, if you want to, right? That could solve a lot of your problems. Yes?
I mean, didn't HTTP 1.1 have the keep alive header that you could kind of use?
Yeah, but you see, those are good if you do rapid fire for a page, but virtually every time you clicked on another URL, that all was taken down. So they try to do some tricks, some things, but they're nowhere close to the cleanness of a WebSocket solution. Not to mention that it's bidirectional communication, which you might want to do in the first place, right? Okay, so why am I telling you that? Because in Scala, yes? Well, a nice implementation of REST interfaces is through WebSockets, but it can be done through normal URLs. Close bracket, let's go back to the class, sorry. All right, so why am I telling you this? Because think about how remote actors might be implemented in Akka. So I'm asking you to use Akka to do remote actors, but I want you to start being aware of what's going on in there. So you have these 2 machines, they're both running Akka, or 10 machines, they're both running Akka, and you can have multiple actors that communicate remotely. How do you implement this? Well, you could get essentially something equivalent to a WebSocket. It's essentially a permanent TCP IP connection between the Akka libraries. They keep it alive, so they have their own little actors that keep it alive. And when an actor here wants to talk to an actor here, they literally give the message to essentially the proxy actor here, who is going to put it on the already open TCP IP connection, and it's popping up in here. This actually tremendously can improve performance of the messaging because it takes a long time to open a TCP IP connection. It's much better if you keep it warm. This is why they're trying to optimize in this way, right? It's much better if you keep it warm and you just send more information on it. Not to mention that TCP IP connections have their own keep alive thing. So if you can detect when a TCP IP connection goes down at either ends, and that's one way to detect if the guy at the other end is potentially doing something nasty. So you don't even need keep alives because TCP IP has keep alives, among other things, right? So this kind of make a single pipe deep in the library and use that pipe for any communication between 2 machines, right? It's actually used by middleware like Akka to provide nice services on top of it. Now here's an interesting connection. Is it better when it comes to speed of communication to have 1 connection or multiple connections with a machine? So is 3 pipes better than 1 pipe? Well, let me give you a hint. Your answer should always be it depends, because virtually everything in this class, it's depends, and everything in the life, it depends. Well, probably the answer is closer to 1 connection because you can actually max out the utilization with 1 connection. Now, there are circumstances, but if done right, not even that's going to be an issue. So if you really have multiple network cards, it might be better to have multiple connections if you ensure that they go out through different network cards. For example, how many of you have 2 internet connections to 2 different ISPs? Well, some crazy people do, just for redundancy or to improve their bandwidth, or to confuse whoever is trying to watch what they are doing. Right? This actually can be done at a very low level in the operating system, in which it's called basically virtualizing the network card. 2 network cards can be virtually looked at as a single network card, and when you send packets, 1 packet goes on one end and 1 packet goes on the other end. Now that's doable with video, but it's not doable with TCP. Well, technically it's doable with TCP IP as well. So you split the traffic and you send it on 2 ways, and then it converges on the other end. Crazy. You need to do this, by the way, if you really want true servers to communicate as fast as they can. You simply put multiple network cards and more wires between them, right? It's called channel bundling or channel bonding, I think. It's a super esoteric, extremely advanced technique to improve bandwidth, but none of you are going to do that, at least not anytime soon. So most of the time, it's enough to have a single TCP/IP connection because it maxes out communication speed, throughput, or whatever between any two computers. TCP is designed to be like that, right? So there's very little benefit in having more than one connection between machines. And then it's easier to manage. Anyway, that's it about all the processes and client server and so on. I'm going to refer back to this material, right? This is the material. I'm going to have a quiz on Saturday. So I'm going to try to be on time and put the quiz by midday on Saturday and give you until Sunday night. It's going to be about processes and threads and all the stuff we talked about. Next week, we switch to communication. And then more and more about issues related to distributed systems. How can you build this nice thing? So